This is part one of the series Logarithmic, Exponential, and Other Transcendental Functions. And as the title states, we're going to be covering logarithmic, exponential, and transcendental functions, or simply functions that are non-algebraic. That is, functions that are not roots of polynomial functions. Let's jump in and start talking about the natural logarithmic function. As you can see, the natural log function has several interesting properties. The first is that it is asymptotic with the y-axis. It's monotonic, and so it's one-to-one and always increasing. And you can see that the slope of the tangent line is going to be positive but decreasing across its domain. So, as you remember from your pre-calculus mathematics, that the logarithmic function has several properties that mimic the properties of logarithmic functions because the natural log is a logarithmic function. It's simply log to the natural number e base. So ln is just log to the base e. So let's take a look at some of the properties of the natural logarithmic function just to refresh our memories. You can see that the first property, ln of 1 equals 0, is evident from the graph. The natural log of 1 is 0, and the natural log function is the inverse of the exponential functions, and therefore a to the 0 power is always going to be 1. So the exponential function would be a reflection across the line y equals x, and so exponential would go through 0, 1, whereas natural log goes through 1, 0. The second property, the natural log of a times b is the natural log of a plus the natural log of b. This is the product rule. And then the power rule is the natural log of x to the n is n, the power, times the natural log of x. And then the quotient rule, the natural log of a divided by b is the natural log of a minus the natural log of b. And we're going to go through and prove each one of these properties, but for now I just wanted to give a quick review of what we learned about natural logs in pre-calculus mathematics. Hopefully you'll recall our initial discussions on integration when it was introduced previously, and we talked about the general power rule for integration. And the general power rule said that the integral of some function to the n power with respect to x is equal to x times n plus 1, that is, we add 1 to the exponent and divide it by that new exponent, plus the constant of integration. And this special caveat is now going to be very important, where n doesn't equal negative 1. What that means is that up to this point we have not been able to take the antiderivative of the reciprocal function. So right now we don't know how to find the antiderivative of this function. But with the help of the natural log function, we're going to see how to do that. Let's start out by considering the equation y equals ln of x. What we're going to want to do is we're going to want to take the derivative of this function with respect to x, but we want to use the limit definition of a derivative. The limit definition of a derivative states that the derivative of a function is the limit as delta x approaches 0 of the function evaluated at some x plus delta x minus the function evaluated at x divided by delta x. Now, what we're going to do first is we're going to take use of one of the properties of logarithms. Notice we have the ln of some value minus the ln of another value. So this is ln of a minus ln of v. If you remember, the quotient property said that the ln of a minus b is equal to the natural log of a divided by b. And so that's what we're going to do, is we're going to substitute this using the quotient rule. So this natural log is equivalent to this logarithmic expression. Now we're going to rewrite this slightly, and this logarithmic function divided by delta x is the same as the product of 1 over delta x times this logarithmic expression. So in essence, that's all we did was put this 1 over delta x off to the side here. Now what I want to do is to separate this expression into two separate terms. So x divided by x plus delta x divided by x. And that gives us x divided by x is 1, and delta x divided by x is just delta x divided by x. Now the next thing I want to do is I'm going to employ another property of logarithms. Here we have 1 over delta x times a natural logarithmic function. So I'm going to use the power rule and turn this into an exponent. So that's all I've done is taken this coefficient, this product up here, and moved it to the exponent here using the power rule of logarithms. So this coefficient moves to the exponent using the power rule for logs. At this point, you may be wondering, what are we doing with all these gyrations? Well, the whole purpose behind this is to manipulate this expression into a special form that we need to get to. That's going to help us in proving our target, which is the connection between 1 over x and the natural log function. So to accomplish that, the next step is I'm going to do a u substitution in here. And what we're going to substitute is we're going to say u is equal to delta x divided by x. Now, if u equals delta x divided by x, then a simple manipulation gives us delta x is equal to u times x. And so we're going to use those two in the next statement. So we're going to replace this with u, and we're going to replace this denominator in the power with ux. And here we have that substitution. We've made that substitution several places. First, we've taken the delta x over x, and we've set it equal to u here. We've taken this 1 over delta x, and we've replaced it with 1 over ux, so delta x is just ux. And then we've taken this and said that since delta x is equal to ux, as delta x approaches 0, that means that ux would approach 0. So some quantity u times some quantity x is approaching 0. Well, if u times x is approaching 0, then that's the same as saying u times anything is approaching 0. We could also say u times 1 is approaching 0. In that case, we would just have u is approaching 0. So that's where this replacement comes in here. And that gives us this simplified version. Now we're going to employ a rule of exponents. Here we have the exponent 1 over u times x. This is simply 1 over u times 1 over x. Well, you know that whenever we have two exponents multiplied together, that's the same as one exponent raised to another, or one expression to an exponent and that whole thing raised to another power. So that's what we're going to do next. We're going to use this exponential rule that a to the xy power is equal to a to the x, that whole thing to the y. So whenever we're raising an expression to a power to another power, those exponents are multiplied. And that's what we're going to do next. Here we have this expression to the 1 over u power, and that whole thing has been raised to the 1 over x power. At this point, we're going to apply a couple of properties. The first one is we're going to use the logarithmic power rule in reverse. So we're going to take this exponent here, and we're going to pull it up front, and then we're going to utilize a property of limits that we've seen in the past. So let's see what that looks like. So here we have the exponent has been applied using the power rule for logs up front. So that exponent is no longer an exponent, it's now up front, the natural log. But also notice what happened here. What we did was we swapped the limit as u goes to 0 with the natural log. Here, the natural log was inside the limit, and here it's outside the limit. And the property that we're using there is akin to this idea, that if we have the limit as x approaches 1 of ln of x, that's the same as saying the natural log of the limit as x approaches 1 of x. Because in either case, the natural log of x as x approaches 1 is ln of 1. And the natural log of the limit of x approaches 1, this can be evaluated directly as x equals 1. So that's natural log of 1. So this is the exact same thing. And the natural log is giving us a value. So this limit, the limit of this value is the same as the natural log of that limit value. That's the two substitutions that we've done here. And now, at long last, we've arrived at our manipulation target. This expression inside here, the limit as u approaches 0 of 1 plus u to the 1 over u power, is one definition of the natural number, e, 2.7182818, and so on. And we know from our basic properties of logarithms that ln is just log to the base e. And we know that one of the fundamental properties of logs is log to the base a of a is simply 1. And because this limit is just one of the definitions of e, we have the following: that the derivative of this original function ln of x is just 1 over x times the natural log of e. And as we just said, the natural log of e is 1, so our final result is that the derivative of the natural log of x is 1 over x. So what this all boils down to is the following. Since the fundamental theorem of calculus tells us that differentiation and indefinite integration are inverses of each other, that because the derivative of ln of x is 1 over x, then the antiderivative of 1 over x must be ln of x. And that brings us to the definition of the natural log function. Using the fundamental theorem of calculus and the concept of a definite integral as a function, we know that the definite integral from 1 to x of 1 over t dt is equal to the natural log of x if x is greater than 0. And now, of course, by extension, this whole process implies that the derivative of ln of x with respect to x is 1 over x, and therefore the derivative of ln of u is 1 over u du as long as u is a differentiable function of x. So this gives us a more general form for the derivative of natural log and also the antiderivative of 1 over x. Now, just to wrap things up, I'd like to show a real quick visual representation of what this whole thing means. So here we have the graph of the natural log function, and here we have the graph of 1 over x. And this value represents the natural log of this x value. So the natural log of 2 is 0.6315, and I can alter that as we go out this way. What this shaded area represents is the area under the curve, that is the antiderivative from 1 to x of 1 over x. And as you can see, the area under the curve is exactly equal to the natural log of the function. So if we set this equal to 2, the natural log of 2 is 0.69315, and the area under the curve, the integral from 1 to 2 of 1 over x, is the exact same value. Unless we doubt one final confirmation, we pull out our trusty graphing calculator, set 1 over x into the function, display the graph, and let's take the integral. And we set our lower limit to 1, upper limit to 2, and you can see that the value is exactly the same as what we have here. Well, that'll wrap up this part, and I'll talk to you in the next video.